commissions who then set up working groups to examine specific problems. So there's a general organic petrology group, geological applications of organic petrology, and industrial applications of organic petrology. And we also have other activities such as accreditation programs, training programs, and we publish materials. So just to give you a quick idea of the sorts of activities that these groups do. So within Commission 1, for example, we have this commission, we have little working groups. What happens at the annual meetings is that the working groups come together, they discuss and talk about the problems and the activities that have been performed during the year, and then make some decisions, hopefully, either to finalise some activities or to continue further work on those particular problems. So the meetings we hold aren't this style of meeting where we have a seminar set up with questions and answers. They're really discussion group forum meetings. And from that point of view, they're extremely useful venues if you have problems that you want to talk to other colleagues about and discuss and try and make some progress on the sites of them. These sorts of venues are almost unique, certainly in the world of coal petrology, where we discuss and talk about things rather than people simply get up and present their own individual research. So there's a whole bunch of what the group's trying to do is get together, lots of different people, lots of different sources, and try and establish some real ground truth in some of the sorts of activities. So they're the sorts of group activities that are probably of more direct interest to the petroleum exploration people. And industrial applications such as through combustion or carbonisation of the coals, and what the coal microscopy can tell us. It's the third commission. We have three very important activities called accreditation activities, and what we do is we accredit people as being able to perform certain sorts of microscopic analyses. These grew out of sort of very bad data sets, I think, of different laboratories giving different data on the same sorts of analysis. So like a vitrite reflectance may have gotten a large number of variable outcomes depending on the laboratory that you use. And what we do is we accredit people to do each of these sorts of analyses. So every 2 years we send a set of samples, we do the work on the sample, it goes back to a convener of the group, and once all the data is collected, it goes to a complex statistical analysis, and you either get accredited to be able to do the work, which means you can measure vitrinite reflectance within acceptable limits on coal samples, or you can measure vitrinite reflectance in dispersed organic matter within acceptable limits, or you can do a different sort of analysis, more a coal blend analysis. So this is very important to make sure that we're giving out reliable data to the users, to the oil industry. They can be sure that if you're using an accredited person, that they are capable of doing this work. We have a whole bunch of publications that come out as well. So the most important is probably the handbook. This is under revision at the minute. But you can see that we talk about coals, the microscopy of the coals, how you utilise the coals, other terms associated with the coal microscopy, methods of polishing and preparation of the samples for use. There is some training materials available for vitrinite reflectance and dispersed organic matter training kit, and some for spectrophorescence measurement. Some of these items are published periodically in international journals such as Fuel or International Journal of Coal Geology, and some of these classifications here, which I've noted there are published, appear in those journals. We have training programs in organic petrology. There are 2 of those available. They're a short course format, 3 to 5 days sort of thing. They can be tailored to meet individual needs. There's one in organic petrology and one in dispersed organic matter. There's a training course in Germany, in Potsdam, very shortly, on the 14th, the 10th to the 14th of June. If anybody's interested in attending that course, it's not too late to register for it. Details can be found on our website. All this information can be found on the website if anybody's interested in pursuing some of these matters. And that's some of the things that will be covered in the training course. We have annual meetings. We like to get around the place. We're a very active group. We like to visit lots of exotic countries. So this year we're off to Poland. Next year we're in India. The following year we're in Mozambique. We normally have every second meeting around Europe, so the 2016 meeting is likely to be somewhere in or near Europe. And people are invited to attend these meetings. Again, you can find any information related to those on the website if people are interested in attending, or if becoming an ICCP member, there are application forms available. Last year we were in Beijing, and you'll probably recognise a few characters in there. Dr. Parker is in there somewhere. I can't see from here. There he is. There he is. Yeah, here. So, we're a very nice group of people. We're very friendly. Nobody bites in particular, and it's a very good forum for exchanging information and getting involved in activities that can benefit your knowledge base and our knowledge base as well. So, thank you for the opportunity to say something about the ICCP, and we hope that we can get some more members from Kurdistan to join the group and actively participate in some of the activities. Anybody have any questions they wanted to ask about the ICCP at all? No? Okay, so I'll start the presentation that I was going to give on some of the research work that I've been doing.
Each has a special or a will of the others and all my
degrees, which is at the boundary between a subbituminous coal and a high volatile bituminous coal. This is a fairly important boundary for lots of biological organisms, as they tend to die at temperatures more than about 50 or 60 degrees, and they can thrive at lower temperatures. And this becomes very important for the coal seam gas industry in terms of biogenic production of methane. So this is just a standard cracking of the hydrocarbons to produce methane.
Temperatures Celsius or Fahrenheit?
Sorry?
In Celsius or Fahrenheit?
Celsius.
Celsius, yeah. If you take some coal samples and you artificially heat them up, so here we've got vitrinite reflectance from about 0.5% to 3.5% or so, and look at the gases that are evolved from them thermogenically, you find that you get very large amounts of gas evolved. So this is around about 350 cubic metres of gas per tonne of coal, which is quite a lot of gas. And considering that the storage capacity for the coal would only be down here somewhere, and probably 40 cubic metres per tonne maximum storage capacity. It means the coals generate large amounts of methane and carbon dioxide thermogenically that can't be trapped and stored by the coals, and have to be released out of the coals and migrate somewhere else in the system, and may be trapped in conventional reservoirs, or may be trapped in coals somewhere higher up, or may simply escape. So one of the key issues here is that we have methane and carbon dioxide, large volumes of it, the storage capacity, the amount of gas that can be stored by the coals down here somewhere, and it can generate many times more gas is capable of being stored by the coal. So most of it is lost out of the system. So that's what we sort of call early thermogenic, so just normal maturation processes. The coal seam gas people like to talk about the late thermogenic process as well. This is a picture from Collinsville in Queensland. It's Permian coals. There's a coal seam, it's about a 4 metre coal seam running through here. There's a thinner coal seam running across the top. All this white material is igneous intrusions that have intruded into the coals. The interaction of the igneous intrusion and the coal produces carbon dioxide in very large amounts and tends to displace all of the hydrocarbon gases. So where this kind of setup happens, we tend to get mostly carbon dioxide in the coals and very little methane at all. This is a very common thing in Australia, in the Northern Bowen Basin, in this Collinsville area. Nearly all the seams are intruded in this way, and it's very common in many of the Permian sequences down the east coast of Australia as well. So there's a Cretaceous intrusion into the Permian, producing large volumes of carbon dioxide. Coals are funny things. They don't like being intruded by igneous rocks, and they become fluid and plastic and can melt and run into the rocks. Here there's the coal seam that's been intruded. This is columnar jointing that's developed within the coal in response to it being devolatilized, and it's producing a natural coke of the coal. Coals are often coked to produce steel in a similar sort of process to this, but that's a natural coating of the coal. And you can see this develop microscopically in the coal. There's a high volatile bituminous coal here. This is the vitrinite component. There's an inertinite. You can see a few little bits of vitrinites in through here as well. That's the same sort of coal that's been heat affected. You see development of these patchy mosaic textures within the coal and much higher reflectance of the coal. A similar piece of coal here. This is mostly vitrinite, and these are pores relating to degasification of the vitrinite due to heating of the coal. So you can see this very readily microscopically. Other sorts of analysis can be very difficult to determine whether the coals are being intruded and being affected in this way.
That's under UV light or?
No, that's a polished, that's about 250 micron field of view. That's polished reflected light oil immersion. It's plain white light. So the microscopy of the coal is a very powerful tool in looking at some of these particular problems. The other thing that's very important with the coal seam gas vehicle is biogenic production of methane. I said earlier on the earlier slide about thermogenic coals up to about 60 degrees, the coals in ground are full of microbes and they can produce large amounts of methane either using an acetate fermentation style reduction or the CO2 reduction to produce methane in both cases. So that's very important in the burial history of the coals when they're being buried to produce methane in this way as well as thermogenically. When the coals are uplifted and they fall back below 60 degrees again, these biogenic processes are again extremely important in producing gas in the coal, the methane. And in many coal deposits, the methane is being produced exclusively by these biogenic processes near the surface, within the few hundred metres of the surface. And most of the thermogenic methane has disappeared altogether. To understand those processes, we need detailed knowledge of the groundwater regime and the hydrology. So we need to worry about multiple different mechanisms for methane formation, in particular in coals, 2 different ways of producing it thermogenically, and 2 different biogenic mechanisms, all of which come into play in different parts of the tectonic history of the seam. The next point I want to make is the storage different to what you'll be used to for natural gas systems here in Kurdistan. The gas that you have, well, most natural gas systems, conventional gas, the gas is present as a free gas, stored in the pore spaces of the rock, or is dissolved within the liquid hydrocarbons. With coal seam gases, the mechanism is completely different. The mechanism of gas storage is one of absorption onto the surface of the coal. So we've got the coal surface here, the gas is stuck onto the coal surface, and that's the way it's trapped in the rock, by sticking onto the surface of the coal by an absorption process. And it's very important to understand that because it means the production methods are very different, the exploration methods are very different for coal seam gas plays as opposed to conventional gas plays. There's a whole bunch of reasons listed there for why we believe that this is the mechanism of storage of gases on coals. And I'm not going to talk about all of them, I'm just going to talk about a couple of them. And this is to try and get you into the frame of mind of thinking about coals as a different substance than different organic substance than the petroleum systems that you may be used to. And the things I'm going to talk about really is the very large storage capacity of the coal in particular, and some aspects about the density considerations of the coal. This is a plot of pressure versus the gas content. Pressure we can also think of in terms of depth from below the surface. In this case, it will be hydrostatic pressure, not lithostatic pressure, that we're considering. And if you took a conventional sandstone with 20% porosity, that black line there is the amount of gas that you can store by compression into the pore spaces. This red line is the amount of gas that can be stored in an equivalent volume of coal with the same pressure. You can see the storage capacity of the coal is extremely large compared to a conventional sandstone. It tells us that the gas cannot be stored by compression. Otherwise, if the gas was stored simply by compression into the pores of the coal, it would be down here somewhere, the storage capacity. It would be the same. It tells us the mechanism is different, and in this case, we're storing the gas in a liquid-like form, absorbed to the surface of the coal. So this is more of a liquid-like gas storage mechanism, and this is a true gas. I wanted to talk quickly too about the density of the methane in particular, and to do that, we need to look at a phase diagram like this, the standard methane phase diagram, temperature versus pressure, vapor, gas, critical point, supercritical fluid, liquid fields. This is the same diagram with a much, a bit more information on it. These lines here are lines of equal density of methane. So they're lines of equal density for methane. To get the sort of storage capacity I showed you on the earlier graph with the red line and the black line, we need to have the methane having this style of density over here. If the methane was present as a gas, it would fall in this field over here somewhere in terms of its density in the ground. So we can see from this plot that to get the right density of the methane, we need to have the methane being stored in some liquid-like manner by the coals. It cannot be present as a gas. That's sort of the point of that diagram. I won't go into that. This is a schematic absorption that you might think of a gas onto a solid, where you may have some absorption sites, and as you're increasing the pressure, increasing the surface area coverage, you get more and more absorption sites until they're all eventually filled, and you're going to have no more absorption in a single layer anymore. And this is an important way to be thinking about gases, because it tells us something about how the density of the methane should vary as a function of pressure. If the density of the methane was constant, then, well, it can't be constant because we have different surface area coverages at different pressures. And if you look at that in a more realistic sort of model, if that was the surface of coal and this is the density areas of the methane, we'd see a very patchy density distribution covering the surface of the coal. So while the methane is present in a liquid-like fashion across the surface of the coal, it's very patchy across the surface of the coal. It's not a uniform film across the surface. I think the last thing we really need to think about with the coals, and this is a thing that's very, very different from the petroleum systems, is the porosity of the coals. Coals are reasonably porous. 5, 10, 15% porosity total is not an unusual number for a coal. But where they're different from a conventional reservoir is that most of the pores in coal fall within this microporous range, less than 20 angstroms in diameter. These are the storage sites for the methane. Now you have to remember, or you have to know, that methane as a molecule is 4 angstroms in size. So if that was 20 angstroms, the methane's only about that big. So these are very, very, very small pores. They're not hundreds and hundreds of microns in size like you might have in a sandstone. They're not 0.1 of a micron in size. These are molecular-sized pores that the methane is being stored in the coal. It's a very, very fine pore structure, and it's the reason the coals store so much gas. So schematically, people used to think about that's the surface, you're getting absorption of gas onto the surface, but really, in coals, we've got a very fine structure where the pore sizes are only a few molecular diameters big. And in reality, the structure of coal looks more like this. A big mess of organic molecules floating around in space. There's 10 angstroms. And within this framework of organic molecules, we sit the methanes. They're sitting within that organic framework. So it's very unlike a conventional reservoir where you have a big sand grain here, another big sand grain over there, big free space in the middle with gas floating around in it. With the coals, the methane is intrinsically associated with the molecular framework of the coal. That's a very complicated three-dimensional model of coal showing the same sort of thing but in a much more complicated way. And a similar thing showing methane molecules, these little starry things, sitting within the three-dimensional framework of the organic matrix of the coal. So very, very different to a petroleum system. Carbon dioxide. Yeah, okay. How much time have I got? Let me just get that out. I'll go quick. I'll wait, let's spend 2 minutes and I'll stop. Okay? I won't really need that. The actual experiment that we did, we were interested in looking at a problem where we had a bunch of samples, we had some test data, the amount of gas present in the coal, the maximum amount of gas was represented by that line. The data suggested we had 200% storage capacity of the coal, which is not possible. We did some additional experimental work. Those are the sort of coals we were looking at, some Indonesian coals. The initial work was done on that kind of modelling. We did a more complicated mathematical model, although still not terribly complicated.
Can you want 5 minutes?
Huh?
5 minutes. You want 5 minutes?
Yeah, this will take me half an hour to do. I'll just finish quickly. We did a much more complicated mathematical model are using a variety of gases instead of simply methane. So in this case, to do this model, we used methane plus carbon dioxide, which was present within the seams, and we produced a new set of curves. This is a methane curve, that's a carbon dioxide curve. This is our data point in here. We see it fits quite closely on this darker line, which is the new model curve from the more complicated equation. That's the same with all of them. That's the problem. So we turn this problem here of having many samples apparently storing more gas than they could possibly ever hold into a much more reasonable problem of the gases being less than the storage capacity of the sample, of the samples. There's only really one conclusion from that, and that's when more than one gas species is present, you have to use these more complicated equations and actually account for the presence of the other gases when you're doing the modelling for the saturation. So thank you very much for your kind attention.
Dr. Peter Koldal, thank you very much for your presentation. And let's start with the questions.
Doctor, a couple of questions. The first one, you mentioned some factors that affect the amount of gas absorbed in the coal bed methane. So one of them, rank of the coal. I'm going to see how rank of the coal, because it's there, the gas. How affects the amount of storage gas? Secondly, we see unconventional petroleum system here. I hope you mention some ways to get out, because it's very impossible to get out any gas. It's unconventional. So, and we know there is gas.
Okay, the first point on how coal rank affects the storage capacity. The way it's affected by coal rank is if you take a low rank coal and look at the pore distribution, many of the pores are in the meso and macro pore categories. These are larger pores that can store gas in a conventional reservoir sense, but can't absorb gas very well. As you increase the rank of the coal, the number of very, very small pores increases and the number of very large pores decrease. This is what happens. So you get more very, very fine pores where we can store the gas in a liquid-like fashion, absorbed onto the surface, and the number of very large pores that would only allow for the gas to be stored by compression decreases. So we increase the storage capacity by changing the pore structure of the coal. And this change in pore structure happens partly in response to devolatilization and loss of some of the molecules while the system is being compressed. So it's a change in the pore structure as you increase the coal rank. Yeah?
What you mean by structure, when you call the structure?
By the pore size distribution.
Not on a graphite or a nanocarbon tube or
No,
something like that?
no.
Just leave them for such.
I will
Wait,
show this tomorrow.
sorry?
I will show this tomorrow.
The dirt will show you tomorrow, apparently, so that's good. We've got much more detail. The other point to your question